In this example video, we have an asteroid of mass 3 times 10 to the 10 kilograms that has a velocity of 1500 meters per second at a distance of 4 times 10 to the 7 meters from the surface of the Earth. The asteroid continues to head directly towards Earth. What is the velocity of the asteroid as it reaches the top of the exosphere, which is 1 times 10 to the 7 meters above the surface of the Earth? Alright, so we're looking at an object that is within Earth's gravitational field, but it is changing distance from the surface of the Earth significantly, which means that our acceleration is not going to be constant. We certainly cannot assume at this point above the Earth's surface that the acceleration due to gravity is 9.8 meters per second squared. So that means that we're going to have to apply conservation of energy, because that allows us to handle non-constant accelerations. We also have to remember that we have to use a different form of the gravitational potential energy equation, because mgy assumes that g is constant. So we have to use the form of gravitational potential energy that allows us to handle a non-constant gravitational field strength. So I'm plugging in to negative times the gravitational constant times the mass of the Earth times the mass of the object, the asteroid in this case, divided by the distance from the center of the Earth to where the asteroid is located, plus kinetic energy, so 1/2 mv squared of the asteroid. And that's going to equal a negative gravitational constant times the mass of the Earth times the mass of the asteroid divided by the distance from the surface of the Earth, plus our final kinetic energy, so 1/2 mv squared again. So I plugged in here the gravitational constant. I looked up the mass of the Earth to plug in. The mass of the asteroid was provided. Now this distance, the 4 times 10 to the 7 meters, is the distance from the surface. So I've added on here the radius of the Earth, which I also had to look up, plus 1/2 times the mass of the asteroid times the 1500 meters per second. I squared that because it's kinetic energy. That's going to equal our gravitational constant times the mass of the Earth times the mass of the object divided by our new distance from the surface of the Earth plus the radius of the Earth. And then we have plus 1/2 times the mass of the asteroid times our unknown velocity squared. So when I solve this algebraically, I get 5.81 times 10 to the 3 meters per second. Now, this problem does ignore a number of items. One, it ignores everything else in the solar system that might have a gravitational influence on the asteroid. It also ignores the fact that the Earth is actually in motion relative to the asteroid, because the Earth is orbiting around the Sun and then the solar system is orbiting around the center of the galaxy. So a lot of these problems, when we're dealing with working in the solar system, are a little more complicated than we actually make them out to be.